Good everyone, my name is Graphics. Today we want to solve another exercise on vapor compression system, which is an aspect of thermodynamics. Now, if you look at this question, it says a vapor compression refrigerator using R134A has the working fluid operates between an evaporator temperature of minus 15 degrees Celsius and a condenser temperature of 30 degrees Celsius. Full stop. Saturated liquid refrigerant enters the throttle valve while the vapor is dry saturated at the entry to the compressor. The process is isentropic. For a refrigeration capacity of 7.5 kilowatts, calculate, we have what is called the mass flow rate, the power input, and the refrigerating efficiency. Now, what you do in this kind of situation is this. We'll draw our Carnot cycle that will guide us. First of all, let's write down our parameters. So, solution. Now, from the question that we have here, is saying that the working fluid of this refrigerator is R134A. That is, the working fluid means the refrigerant, the system of the compression system, which is the refrigerant. Now we'll write it this way by saying my working fluid, the working fluid, right, which is we'll call the refrigerant, is giving us what? The R134A. Now we move. Now it says the working fluid operates between evaporator temperature of minus 15 and condenser temperature of 30 degrees. So you write evaporator temperature is, we call it TL, is giving us what? Minus 15 degrees Celsius. So the upper temperature is always the low temperature, right? Then the next one is the condensing temperature. We'll call it condenser temperature. So I have my T, then the E here. We'll call it TH, as giving us what? 30 degrees Celsius. Similarly, we are told that saturated liquid refrigerant enters the throttle valve, and so on and so forth. Then in this aspect here, it says saturated liquid refrigerant enters the throttle valve while the vapor is dry saturated at the entry to the compressor. The process is isentropic for refrigeration capacity of what? 7.5 kilowatts. So we are going to write that our refrigeration capacity, which is giving us R.C, is giving us what? 7.5 kilowatts. So after doing this, what you need to do, then I told us to calculate what? The mass flow rate. We are looking for our mass flow what? Flow rate, which is giving us small m with a dot on it. We're looking for that. We're also looking for the power input. Right, we'll give it as our work rate. That's what power input is. So we're looking for that too. And also the refrigerating efficiency. So the refrigerating efficiency. So that's giving us this guy. And we have R. So we're looking for that too. So we'll start. This is our data given. So let's start moving. The first thing you do here is to draw your TS diagram, which is like this. And like this. So from here, this is T, this is X, the entropy, which is given in kilojoule per kilogram Kelvin, and we have the temperature, which is given in degrees Celsius. Now we'll draw our dome this way. That okay? Now to guide you is this. Let's draw our Carnot cycle. We have something like this. Which is giving us our condenser. I will have another one just below it, which is giving us our evaporator. And we have this connected in this way. And that will give us as what? Our compressor. Now this connected in this way, that will give us as our expander. So from here, at this point, here we call it state 1, which is the entry of the compressor. Is that the key? This is the entry of the compressor. Here, call it state 2, which is the exit of the compressor. Here, we call it state 3, the exit. The exit of the compressor is the entry of the condenser. Then state 3 is the exit of the condenser, which is also the entry of the expander. Then we have state 4, which is the entry of the evaporator, which is also the exit of what? The expander. Now, one thing you need to know, when you have this, you draw your line this way, and also draw your line this way. The top here is giving us our TH, which is representing the temperature of the condenser, right? Now, the down one here is giving us TL, which is called the low temperature, which is the temperature of what? The evaporator. Now, at this point here, from this is where this line you see, we call the dome, is called our saturated line. Whatever value that falls on this line is seen in the steam table. We say that everything on this line is saturated. Anything outside this line is superheated. Are we together? Now, at the left hand side, at the right hand side there, everything you see here will be called a gas. At the left hand side, everything you see will call a liquid, a fluid. While in the middle is also a gas, that is F and what? And G. Right? Now, if you look at this point here is 1, which is equivalent to this entry point of the compressor. This point here is like 2, which is equivalent to what? The entry of the condenser, which is also the exit of the what? Compressor. Here is like saying 3, which is the exit of the condenser, and we have 4, which is the exit of the expander, which is also the entry of what? The evaporator. Now, what you do here is this. In our question, one thing you need to know, from this side down here, we say it is what? Gas. So anything that falls from here down here is gas. Anything that falls from here down here is what? Liquid. And anything that falls in the middle is what? Both gas and liquid. That's why they call this region the wet region. So from our question here, it says that the vapor compression refrigerator using R134A as a working fluid operates between an evaporator temperature of -15, right, and a condenser temperature of 30 degrees Celsius. He said saturated liquid refrigerant enters the throttle valve. Now what you look is keyword. He said saturated liquid refrigerant. So the keyword is that what? The liquid, meaning that it's falling on the left hand side. Saturated means that it's falling on the line, right? And he said it enters into what? It enters into the throttle valve. Now they have modified the Carnot system. They have replaced the expander with what? A throttle valve. So the entry of the throttle valve is at the expander here. The expander now is not the throttle valve. So the entry is 3, and this is 3. So this point says our what? Our point 3, because it says saturated liquid refrigerant enters the throttle valve. So we replace the throttle valve, the expander, by the throttle valve, right? So if I like, I can just remove this expander here, and I'll put what? Throttle valve. Not so that to not confuse you. Is that okay? Now we'll move forward. From here now, it says it enters what? The refrigerant enters the throttle valve while the vapor is dry, saturated at the entry to the compressor. Now it says the entry, it says saturated vapor which is dry at the entry of the compressor, which is state 1. So at this point here is the entry of the compressor. So if I trace this down this way, and I trace it to this point, and I trace it straight up to meet this here, right? This will now be, I'll call it my 2, or would I just say maybe my state 2 here. I'll call it my state 2. Then this is what we have. So it is falling outside this dome here. So it means state 2 is what? Superheated. So I'm going to put my arrow this way to show the direction of my movement. So you say this is giving us -15 degrees Celsius, and it's giving us what? 30 degrees Celsius. So from here, what you do to avoid confusion, this is 1, you change, this is what? 2, right? Then you change this to what? You can just leave this. You come to here, this is 3, right? This is what? 4, and this is what? 5. Or what will I say? This is 1, this is 2, change here to what? 3, make here to become 4, then here will be what? 5, then this point will be what? 6. So let me just remove this. So you just rename them. So let's move forward now. Now I'm moving forward. We need to write the value. So we should look for what? The first thing to look for at this point here, we say S4 is equal to what? X6. At this point here, we say X1 is equal to what? S2. Now we move forward. From this spot, we are told to calculate what? The mass flow rate. the what? The mass flow rate. When they say isentropic, that means it is a reversible adiabatic system. So now we say we look for what? Mass flow rate. So I'll come here, I'll leave it this way, right? So what I will do is, alright, calculating for mass flow rate. So we have calculating for mass flow rate, right? We know that, recall, my mass flow rate is equal to what? Refrigeration capacity over what? Refrigeration effect. From our parameters here, we say that the refrigeration capacity is what? 7.5 kilowatts. So I'll say this is equals to what? 7.5 all over refrigerating effect. Refrigerating effect is also called the cooling effect. And where can you see the cooling effect? Cooling effect is always at the what? The evaporator, right? And evaporator is between state 6 and state 1. So what we'll do, it will be, the refrigerating effect will be H1 minus what? H6. It will be H1 minus what? H6. H means the enthalpy. Enthalpy is the energy, right? So the energy at state 1 minus the energy at what? At state 6. So I'm going to call this my, I'm looking at my equation what? My equation 1. Instead of using do that, before you do all of this, right? You first of all write all the values of your entropy and what? Your enthalpy. So that is what I'll do. Then I'll come back to this point here. Now at this point, if I calculate for my enthalpy at state 1, let's see. So calculating for entropy at each state, calculating for entropy at each state. So let's see how it goes. So what we'll do is, you only focus on the entropy that is what? Saturated. So at this point it's saturated, that is 0.1. So I'm going to put S1 first equals to, the next point that is saturated is at what? 0.3. I'm going to put X3. The next one that is saturated is at what? 4. I'm going to put S4. The next one that's saturated is 5. I'm going to put X5. Right? So now that is all the point that is on the dome. Now if you look at this, I said anything that falls at the left hand side, the right hand side is gas, and S1 falls at the left hand side, on the right hand side, and S3 also falls at the right hand side. Because when you divide this into two, this is the right hand side and this is the left hand side. So means since S1 and S3 are falling there, both of them are Sg, they are gas. So entropy at state 1 is a gas, entropy at state 3 is also a gas. Now at state 1, what is the temperature? The temperature at state 1 is what? Minus 15. So I'll put Sg at state 1, this is at minus 15 degrees Celsius. At state 3, we trace it, this is 30. So it will be Sg at 30 degrees Celsius. Now for S4 and S5, state 4 and 5 is falling on the left hand side, and that is what? A fluid, a liquid. So you are going to put SF for both of them. So I have my SF and my SF. So at what temperature are they? So for 4 is at 30, so SF at 30 degrees Celsius, and 5 is at what? Minus 15 degrees Celsius. So looking for the value of this. So you now take your steam table. This is where your steam table will come in. So let's see. Now the first thing you check on steam table, you need to check what is the refrigerant. The refrigerant here that is given is what? RU134A. So you go to your steam table and search for the top right corner, look for the RU134A, which is this, and it's what? Tetrafluoroethane. That is RU134A. Now, what we are looking for actually, we are looking for Sg at what? Minus 15. Let's see that again. Sg at what? Minus 15. So you now go on your steam table and search for the temperature of minus 15 on this bar here. So if you are coming down, this is what? Minus 15 here, right? So you trace it to what? Look for Sg. This is Sg here. So you trace it down. Sometimes it's always good for you to use maybe a meter rule or anything to trace it. So when you trace it down, you'll be having this. So you're tracing it down from minus 15, you can see, with your meter rule. So everything that falls on the ruler is minus 15. This is Sg here coming down to this point. And what do we have? 1.7365. So you go and write it 1.7365, 1.7365 kilojoule per kilogram Kelvin. That is the unit. You look for Sg at 30 also, the same thing. Now you trace it. At the temperature we're looking for 30. This is minus 30, not 30, so you still be going down, and you're going to trace 30, right? And if you look at it very well, this is the temperature of 30 at this point here. So I'll take my meter rule, I'll put it under the 30 directly, you can see that, and I'll go to Sg at 30, and that is what? 1.7142. You can see that. This is what we have here. So 1.7142, 1.7142 kilojoule per kilogram Kelvin. Now the same thing, you go to SF at 30 degrees centigrade. SF. So you go to SF, use your meter rule, and you place it there, and you trace SF at 30, and we have 1 point. This is 30 here, right? So we have 1.1434. So I'll go at that point, 1.1434, 1.1434 kilojoule per kilogram Kelvin. Now the same thing you apply to SF at minus 15 also. Now this is minus 15, and you trace it with your meter rule the way I was showing you. We have SF at minus 15. So this is my SF here. I'll go to minus 15, and that is what? 0.9256. 0.9256 kilojoule per what? Kilogram Kelvin. So I've calculated all the values for that. I'll also do that for what? For enthalpy. So let's move that and do for enthalpy and see. So for enthalpy, for what? For enthalpy values, right? So just like we have S1, S3, S4, and S5, we also have H1, H3, H4, and what? H5. So this will give me this. Just like we have SG, we'll be having HG, HG, HF, and what? HF. Just like this. But you change the value to H. Now, just like we have minus 15, 30, 30, minus 15, we also have at minus 15 degrees Celsius, at 30 degrees Celsius, at 30 degrees Celsius, at minus 15 degrees Celsius. So we're going to look for the values of each of them. Now, looking for the values of each of them, we'll visit our steam table. Now, for the steam table, we want to look at H1 at minus 15. So you take your ruler and you place it here. This is minus 15, and you look for, this is the value of H. This is HF. H1 is HG. So we'll come here. What do we have? 389.49. We have 389.49 kilojoule per kilogram. There. The next one, I'll look for what? HG at 30. So visit our steam table. So this is the table of 30 here. Right. Then we'll come here, we'll trace it, and we'll go HG at 30, and that is what? If you trace it, that is 414.74. 414.74 kilojoule per kilogram. Then the next one is what? HF at 30. You visit the same table, so you look for HF at 30. This HF at 30, and that is what? Trace it, 241.69. We have 241.69 kilojoule per kilogram. And the next one is HF at minus 15. You check on the steam table. So HF at minus 15, this is minus 15 here. We have HF. This is HF here, and I will have what? 180.16. We have 180.16 kilojoule per kilogram. So we've gotten all our values. So these are the values we'll be using. So we'll now go back. So after this stage, the next stage we'll still calculate for what? Our mass flow rate. Right? So the first question is that calculate for mass flow rate. So the mass flow rate is given as what? Refrigeration capacity over refrigeration effect, and our refrigeration capacity is 7.5 as given in our table, our parameters, 7.5 kilowatts. Then they will now write that this will now be equals to 7.5 divided by what is H1. H1, you check here, H1 is this, and that is what? 389.49. So you write 389.49 minus H6. Now if you check here, we don't have any H6. Can you see there's no H6? But we know that since my S4 here, since my S4 is equals to X6, so H4 is also equals to what? H6. So that means my H6 here is equals to what? H4. So what do we have there? That is 241.69. So we are going to write it there. 241.69. 241.69. And this will now give me 7.5 divided by, you pick up your calculator, and if you press 389.49, we have 389.49 minus 241.69. That will give me 147.8. So I have my 147.8. So if you divide 7.5, divide 7.5 divided by 147.8, we're going to be having 0.0507. So we see that we have 0.0507 kilogram per seconds. That will be my mass flow rate. Is that okay? So this is our mass flow rate. Now we've got a mass flow rate. Then the next thing that we are told to calculate here is the power input. So if you look at this, we are told to calculate for what? The power what? The power input. You can see that? Power input, which is, we are looking for our power input. So we'll come and do it this way. From here, I'll write calculating for power input. Calculating for power input, which is giving us our work rate, right? So we say that recall the work rate, which is power input, is equals to what? The mass flow rate multiplied by what? The work net, right? So we can say that my work rate is equals to mass flow rate multiplied with the work net. What is doing work in this system? It is the compressor, and the net work at the compressor is what? Between state 2 and state 1. So the higher energy, H2 minus what? H1. H2 minus what? H1. So I will come and I'm going to write that W12, that is the work net. Now we don't know W12, so I will call here to be what? My equation what? Equation 1. Now what I will now do now is that I will now write calculating for what? W12. Is that taken? So we'll put recall W12, the work transfer, is equals to H2 minus what? H1, just like I showed you earlier, which is this H2 minus H1. Higher temperature to what? Minus lower temperature, or higher state minus lower state. So from here, if you look at it in our parameter, we have H1 but we don't have H2. Why? Because H2 is superheated. Earlier I said whatever you see on this dome here is found in the steam table, but anything outside the dome is not in the steam table. So H2, we don't know H2. So what I will do here is that I will turn here to be what? Equation what? Equation 2. So I will say calculating for enthalpy at state 2. So that is H2. Is that okay? So from that point, I'm going to say that my H2 is equals to my Hg plus my H2 into bracket X minus what? Sg. It is superheated. So we're using that formula. This formula is gotten from H is equals to what? Hf plus S into bracket what? Hg into bracket what? Hg minus what? Hf. So this is it. But in this case, since it is superheated at state 2, there will not be any trace of what? Of liquid. It is just pure gas. That is why we allocated every value of what? Liquid, and leave gas. The one that is a gas will not be superheated gas. Now I will call this, I can now rewrite this, that H2 is at what state? If you look at H2, we're looking for H2, right? H2 is at what state? That will be Hg at, so we're looking for H2. So you check here, H2, the temperature of H2 is what? Is 30. So the total temperature of using there will be what? 30 degrees Celsius. So I'll say Hg at 30 degrees Celsius plus S2 into bracket x minus x at 30 degrees Celsius minus Hg at 30 degrees Celsius. Is that taken? So I'm going to call here my equation what? Equation 3. So if you look at this value now, we don't know what our dryness fraction is, S2, right? So what we'll do is we'll write this way that what? Calculating for dryness fraction. Calculating for dryness fraction as state 2, that is S2, we're going to using a entropy relation. So which is saying that my S2 is equals to what? Sg plus S2 into bracket what? S minus Sg. Just like this, but we'll change the value to what? X. This is the enthalpy relation, this is the entropy relation. So from here, we'll start. We know very well that our S2 is not given, but from our TS diagram, the S1 is equals to what? S2. And what is S1? S1 is at what? The minus 15 degree. So I'm going to put that S2 is equals to what? S1 at minus 15 degrees Celsius, right? Equals to what? Sg, it will not be this temperature we're using now, at 30 degrees Celsius plus S2 into brackets S at 30 degrees Celsius minus Sg at 30 degrees Celsius. Is that taken? So let's put our value. We say S2 is equals to S1. Now what is S1 from our table here? The S1 from our table here at 30 degrees Celsius, S1 at minus 15, yes, is given as 1.7365. So I'm going to input it here, 1.7365. to have 1.7365 equals to Sg at 30. So we have Sg at 30. This is Sg at 30 here, and that is what? 1.7142. So we have 1.7142 plus S2 into bracket. We don't know what this guy is. I'll leave a space for it first. Minus Sg at 30, which is also 1.7142. Now, what am I going to use here? This is S at 30 degrees Celsius, right? Now, we'll go to our steam table. The value of X is superheat, means superheated steam, right? And this is the table for superheated steam. Now we say S at what? At 30 degrees. So let's see, first of all, let's go to what? To the 30 first. Now this is 30 here, right? If I use my rule and I place it at 30, I'm going to have this, right? So we're going to look for S. This is for X, and this is also for S. So we have S10K and S20K. So what I'm going to do here is I'll take my paper for S10K. I will have S20K. This is 10K and this is S. This is 20K and this is S. So I'll look for the value of X at 10K. The value of S at 10K is 1.7482. So I'm going to write it 1.7482. and for 20K is what? 1.7803. If you trace it, this is X here, carry it down here, 1.7803. So I'm going to write it 1.7803. Is that okay? So now I'll go back here. Initially we said that S1 is equal to S2, and S2 is superheated. Now you now compare the value of S1 here with the value you have here. That will tell you what this guy is here. So if you look at now, my S1 here now is my S2 here now, my value must be closer to what? My S1. So my S2 here that I will use here is 1.7365. 7365. This is just my normal value that I'm using. So my superheated steam will be closer to this value. So if you look at this, and this, which one is closer? You discover that after this value we have this, then followed by this. So you always take the value that is direct greater than the value that you have as your S1, right? So this is after this we have this, so to be the one on top of it. So if I'm to arrange them now, I'm going to have 1.7365, I'll have 1.7482, and I'll have 1.7803. You see, it is going like this. So you just take the one that is what? Directly up on top of it. You can't jump from here to here. So we have what? 1.7482. So I'm going to go and write it here that this will be 1.7482, right? So if you look at that, 1.7482 is at S10K. So I will now write what? 10K here, right? And I also come to this HG here too and write what? 10K here too. So we'll move forward. So from here, I'll take this 1.7142 to this side. So I'll have 1.7365 minus 1.7142 equals to S2 into bracket 1.7482 minus 1.7142. So if you subtract these two, we'll be having 0.0223 equals to S2 into bracket, you subtract this one too, these two. So if you press that, you'll be having 0.034. So if you divide both sides, my 0.0223 divided by 0.034 will give me my S2. So my S2 will now give me 0.0223 divided by 0.034, and that will give us 0.6558. We have 0.6559. Let me put it that way. The next fraction doesn't have any units. Now you now substitute S2 into equation 3 to get your H2. So we say that substitute S2 equals to 0.6559 into equation 2 into equation 3, right? So let's do what's my equation 3? This is what we have here, and that is what H2 is equals to, you look at Hg at 30. Hg at 30 is, let's see, Hg at 30 is what? 414.74. So I'm going to write, to replace this guy, so now be 414.74 plus S2. S2 is what? 0.6559. Open the brackets. Then we'll look for the next one is, this will be H. This place here is not just X, everything will be H. So we have my H here, right? And we also have what? My H here. Also, we have the H10K here, and we also have the HG here. Is that taken? So from here, my H10K, we'll go and check your steam table for H10K. So I'll come here, you look for H10K at 30. So H10K at 30 will be, you just place it here, right? So if you look for this 10K, is H in front here, and that'll give me what? 425.21. 425.21, right? Then minus HG at 30. HG at 30 is the same thing as this value here, and that is what? 414.74. So if you subtract, so we'll be having my H2 to be equals to 414.74 plus 0.6559 into bracket. If you press this 425.21 minus 414.74, so we have 10.47. So when you multiply them, my H2 will give me 414.74 plus, so you multiply this by 0.6559, and that gives me 6.87. So we have 6.87. So if you add both of them together, the H2 here will be giving me plus 414.74, and that will be 421.61. So we have 421.61 kilojoule per kilogram. That is my H2. Now the next thing you do, you substitute H2 into equation 2. So I'll write it there. Substitute H2 into equation what? Equation 2. So in doing that, we are going to be having W12 equals to what? H2 minus H1. So what is H2? The H2 value I have is 421.61, 421.61, right? And the H1 value I have is 389.49. So have 389.49. So this will now give me minus 389.49. That is 32.11.11, 32.11 kilojoule, right? So we've gotten that W12. So you now substitute, this is my W12. So substitute W12 into equation what? Equation 1. So we're moving up. So this is my equation 1 here. This is what we have here, equation 1. So my work rate will now give me what? Mass flow rate times W12. So what is my mass flow rate? My mass flow rate is given as 0. We have it earlier, which is 0.0507. So we have 0.0507 times W12, which is 32.11. So that will give me times 0.0507. So my value will give me 1.62 kilowatts. That will be my what? My work rate, which is the power input. Alright? So from here, the next thing is to calculate for the efficiency. Calculating for the efficiency calculating for what? Efficiency. Efficiency, that is this. We'll say that my efficiency will give me the C.O.P of refrigerator all over the C.O.P of carnot refrigerator, right? So from here, the C.O.P of refrigerator, we know that recall C.O.P is equals to desired effect, the refrigerating effect all over what? The work net, which is W12. Are we good? So from here, what is the other effect? The other effect is also called the refrigerating effect. All over what? The work net is what? H2 minus what? H1. Now, what is the effect? What do you really want from a fridge? You want cooling, and the cooling is found in the evaporator. So what is the evaporator here? The evaporator is, look at this, my refrigerating effect here is what? H1 minus H6. H1 minus what? Minus H6. And what is H1 minus H6? That is what? 147.8. So I'm going to write it out here. This will now give me 147. Refrigerating effect is 147.8. 147.8 all over H2 minus H1. The H2 minus H1 we'll have here is this is H2 minus H1, and that is what? 32.11. So I'll put it there, 32.11, and this will now give me, that will be 4.60 no unit for it. So this is the COP of what? The refrigerator. Now we want to do for the COP of the carnot refrigerator. So for COP of the carnot refrigerator will give me what? The refrigerating effect, which is the low temperature, all over the work net, which will be the high temperature minus the low temperature. That is the work net there. So this will now give us the low temperature is minus 15. We convert it to Kelvin. So minus 15 plus 258 all over TH minus TL, which will be 30 minus 15. So convert to Kelvin. TH is 30. If you add 273, we have what? 303 minus what? 258. That's my TL. And this will now give me minus 303. That is, we'll be having 258 over 45. So 258 divided by 45 is 5.73. So we have this to be equal to what? 5.73. So we now say therefore my refrigerating capacity, my efficiency will now give me the COP R, which is giving us 4.6. Giving us what? 4.6 all over the COP carnot. The COP carnot, which is giving us 5.73, and this will give me 4.6 divided by 5.73. So we have, this will be 0.802. So we have 0.802, which is something as saying 80.2%. So that is our efficiency. So if you found this video helpful, please don't forget to click on the subscribe button. Thanks for watching.